Suppose I ask you a very simple question. How does one object affect another? Not what happens, but how it happens. If I push a book across a table, that seems straightforward. My hand touches the book. Contact. No mystery. But now, let's make the problem only slightly harder. I put a magnet near a piece of iron. The iron moves. Nothing touches it. There's empty space. In between, still something clearly happened. So now the question becomes unavoidable. What crossed that empty space? For a long time, people were uncomfortable with this question. They preferred not to ask it too carefully. The old idea was simple and appealing. Objects influence each other directly. One thing reaches out and pulls another. But if you slow down and insist on understanding the mechanism, this picture begins to wobble. How does the magnet know the iron is there? Does it send a message? If so, how fast does that message travel? And through what? Exactly. Does it move? This discomfort wasn't limited to magnets. Gravity had the same problem. The earth pulls the moon. The sun pulls the earth, and everything pulls everything else. But how? Isaac Newton himself, who wrote down the law of gravity, was deeply uneasy about the idea that one object could act on another across empty space with no intermediary. He calculated, beautifully predicted motions perfectly, and then admitted, quite honestly, that he did not know the underlying mechanism gravity worked. That was enough to compute orbits, but it did not yet make sense. This tension between being able to calculate something and actually understanding it runs all through physics, and the idea of a field was invented precisely to resolve this tension. To see why, let's take a step back and ask a different question. What do we mean by empty space? We say space is empty when there's no matter in it, no atoms, no dust, no air. Why empty space can't be truly empty. But is that really the end of the story? Or is it possible that space itself has properties even when there's nothing in it? Imagine placing a small test object, say a tiny charged particle, at some point in space. Now observe what happens. If it accelerates, something must be acting on it. You didn't put another object there. So, instead of saying some distant object is mysteriously pulling on this charge, you can say something different. The space at that location is in a certain condition. That condition determines what happens to the particle. This is the first key idea of a field. A field is not a thing sitting in space like a rock or a table. It is a description of the state of space itself. At every point in space, you can assign some quantity, a number, a direction, or both. That tells you what would happen if you placed a suitable object there. For an electric field, that quantity tells you the force a charge would feel. For a gravitational field, it tells you the acceleration a mass would experience. You don't need the object to be there for the field to exist. The field is already there, quietly everywhere. This shift might seem subtle, but it's profound. Instead of saying the sun pulls the earth, you say the sun alters the gravitational field of space around it, and the earth respond to the field. At its location, the interaction is no longer a mysterious long-distance handshake. It becomes local. The earth only responds to what is happening right where it is. Why is that important? Because nature seems to insist on locality. Things influence nearby things, and any influence takes time to propagate. A field allows that. If the sun were to suddenly disappear, a strange thought, but a useful one, the change in the gravitational field would not be felt instantly everywhere. It would move outward at a finite speed. Space itself would adjust point by the birth of the field concept. Point now, historically, this idea did not arrive all at once. It emerged slowly, pushed forward by people who were trying to make sense of experiments that refused to fit the old picture. Take electricity. Early experiments showed forces between charges that looked very much like gravity, stronger when closer, weaker when farther apart. One could have stopped there and said, fine, another action at a distance force. But experiments kept getting more interesting. Moving charges produced magnetic effects, changing magnetic. Situations produced electric effects. The forces were directional. They twisted needles. They induced currents. Something rich and structured was happening in the space around the charges, not just at the charges themselves. So instead of focusing on the objects, physicists began to focus on the space between them. Imagine sprinkling tiny compass needles throughout space near a magnet. Each needle lines up in a particular direction. Draw arrows showing those directions. You've just drawn a picture of a magnetic field. Notice something important. The field is not the magnet. The magnet is just the source. The field exists everywhere around it and has its own pattern and structure. You can even do this without magnets. Think about temperature. A room has a temperature at every point. You don't need a thermometer at every location to talk about the temperature field. The thermometer merely reveals what was already there. In the same way, a charged particle or a mass is like a probe. It tells you what the field is doing at that point. This analogy is helpful because it removes some of the mystery. We are used to the idea that space can have properties. Hot here, cold there. A field simply extends this idea to forces and motion. But now comes a deeper question. Is a field just a mathematical convenience? Or is it something physically real? At first, many people hoped it. It was just bookkeeping. Instead of calculating forces between electric and magnetic fields explained simply, many objects, you calculate a field once and then see how things respond to it. That's tidy and efficient over time. Experiments began to suggest that fields are more than just a trick. Fields can carry energy. They can carry momentum. They can vibrate. They can even exist in regions where there are no particles at all. Light itself turned out to be an electromagnetic field. Moving through space, no charge is required once it's been created. Just the field oscillating. This was a remarkable realization. What we once thought of as nothing, empty space, turned out to be capable of supporting waves, storing energy, and transmitting. Influence. Space was no longer a passive stage on which physics happened. It became an active participant. At this point, it's tempting to ask, what is the field made of? Is it a substance, a medium, a kind of invisible material? This is where we must be careful. History is full of wrong turns caused by insisting that every new idea must resemble an old one. People once imagined a substance called the ether, filling space, vibrating to carry light. Waves like air carry sound. That idea turned out to be unnecessary and misleading. The field does not need to be made of anything in the ordinary sense. It is a fundamental entity. Asking what it's made of may be like asking what numbers are made of. What matters is not what the field is in some philosophical sense, but what it does and how it behaves. Physics progresses not by naming the ultimate substance of reality, but by discovering reliable rules that connect observations. So let's focus on what fields allow us to do. They let us replace mysterious, distant influences with local interaction. They let us describe change propagating through space at finite speeds. They unify seemingly different phenomena, electricity, magnetism, light, into a single framework, and they force us to rethink what we mean by nothing, light as a moving field. But there is still something unsettling about all this. If fields exist everywhere, even in empty space, then the universe is never truly empty. And if particles are just things that respond to fields, and sometimes excitations of fields themselves, then maybe the particles are not the most fundamental actors after all. This brings us to the edge of a much bigger idea, one that changes how we think about matter, forces, and even reality itself. If space can have fields and fields can carry energy, move and interact, then what exactly is a particle? And could it be that what we call objects are merely special behaviors of something deeper and more continuous? That question is not just philosophical. It reshaped physics in the 20th century. And once you take it seriously, you can no longer look at empty space or at objects quite the same way. So before we go any further, here's the question to hold on to. If forces don't act across space directly and space itself can carry influence, energy, and structure, then is the field more fundamental than the things we thought were doing the acting? Let's pick up exactly where we left off. F space can carry structure, energy, and influence if it can have a condition at every point. Then we are forced to reconsider something we usually take for granted, that objects are the basic ingredient of the universe after all. That's how we instinctively think. We imagine a world made of little bits of matter, particles flying around, bumping into one another, pulling and pushing through forces. Fields in this picture are secondary, convenient, useful, but not really real in the same sense as particles. Now, here's the uncomfortable part. Modern physics quietly reverses that picture. Instead of particles creating fields, it turns out to be far more accurate say that fields come first and particles are what we observe when fields behave in certain localized, quantized ways. That's a strong claim when fields become more real than particles. So let's not rush it. Let's see how. Nature pushes us there step by step. Start with something familiar. Waves on water. You don't think of a wave as a thing separate from the water. It's a pattern, a motion of the water. If you ask, what is this wave made of? The answer is simple water, but the wave itself is not a chunk of water traveling across the ocean. The water mostly stays where it is. The pattern moves. Now imagine you see a sharp localized ripple moving across the surface. It's tempting to treat it like an object, but it isn't. It's a temporary structured behavior of a continuous medium. Fields behave in a surprisingly similar way. An electromagnetic field fills space when it oscillates in a particular pattern. We call that light. When that oscillation is localized and quantized, when it can only exist in discrete packets, we call those packets photons. But the underlying entity is still the field. So when you see a photon detected at a point, what you are witnessing is not a tiny billiard ball arriving there. You are seeing the electromagnetic field interacting with matter in a discrete way. This is not a matter of interpretation or philosophy. It is forced on us by experiment. In quantum physics, particles do not behave like solid objects moving along definite paths. They spread out. They interfere with themselves. They behave like waves until they don't. The only description that consistently works is one where the fundamental entity is a field defined everywhere, and what we call a particle is an excitation of that field. Every type of particle corresponds to its own field. There is an electron field, a quark field, a neutrino field, even empty space by this account is not empty. It is a collection of fields in their lowest energy states. This is why the word field becomes unavoidable. You can try to avoid it, but the mathematics and the experiments won't let you. Now, this raises a subtle but crucial point. A field is not just a static background. It is dynamic. It can change with time. It can interact with other fields. And, most surprisingly, It can fluctuate even when nothing seems, quantum, M fields and the vacuum to be happening. Even in its lowest energy state, a quantum field is not perfectly still. It jiggles, not because of external disturbances, but because the laws of nature forbid it. From being completely motionless, this is not noise. It is intrinsic. So, when we say vacuum, we don't mean nothingness. We mean the ground state of all fields, a condition with structure, energy, and consequences. This explains something that would otherwise be deeply puzzling. How particles can appear and disappear in certain conditions. Energy supplied to a field can cause it to produce excitation. Particles out of what we would have once called empty space. Later those excitations can vanish back into the field. Nothing is being created from nothing. The field was there all along. Notice how different this picture is from the old mechanical worldview. Instead of a universe built from tiny solid pieces, we have a universe built from continuous entities with discreteness emerging only in how they are excited and observed. At this point, it's natural to feel a little uneasy. Fields are everywhere. They are invisible. They cannot be picked up or pointed to in the ordinary way. And yet, we are being asked to treat them as the most real things there are. So how do we know we are not fooling ourselves? Because fields do something very important. They make precise predictions that no object-based theory can replace. They tell us exactly how fast influences propagate. They explain why electromagnetic effects travel at the speed of light. They predict new phenomena, waves, radiation, interference patterns that are later observed with extraordinary accuracy. They unify forces that once seemed unrelated, and perhaps most tellingly, when we try to remove fields from our theories and talk only about particles interacting directly, the mathematics becomes inconsistent or meaningless. Fields are not an optional extra, though. They are the language nature uses. Now, let's return briefly to gravity, because it completes the picture. Gravity was the first force we learned to describe mathematically. Gravity as the structure of space, but it was the last to fully accept the field viewpoint. For a long time, gravity looked like a simple pull between masses, but eventually, experiments forced a deeper interpretation. Instead of a gravitation force acting through space, we now describe gravity as a property of space itself, its geometry. Mass and energy change the structure of space, and time and objects move in response to that structure. Once again, the influence is local. An object reacts only to the condition of space where it is. In this sense, gravity is not even a force in the traditional meaning. It is a manifestation of a field, one that defines what straight lines and time, intervals even mean. So whether we are talking about electricity, magnetism, light, or gravity, the message is the same. Space is not a passive void. It has properties. It responds. Yes, it evolves. And now we reach a turning point. If fields are everywhere and particles are excitations of fields, then the universe is less like a machine made of parts and more like a continuously active system, structured by rules rather than pieces. This doesn't make reality vague or fuzzy. On the contrary, it makes it more precise. Fields obey exact equations. Their behavior is constrained. They don't do whatever they like. They do what the laws demand. But it does change how we should think. Instead of asking what objects are interacting here, we ask what fields are present and how are they configured. Instead of asking what force is acting across this distance, we ask how does the field change from point to point. And once you adopt this viewpoint, a remarkable thing happens. Many mysteries stop being mysteries. They become consequences. So here's the question that naturally comes next, and it is the one we cannot avoid if we want to go deeper. if the universe is fundamentally made of fields, not objects? If particles are just special disturbances of something, continuous, then what? Does that say about matter, identity, and the very idea of things existing at all? We begin with a simple discomfort. Objects seem to influence one another across empty space, and no one could quite explain how. What this means about reality itself, discomfort turned out to be a clue. By following it carefully, without rushing, without hiding behind formulas, we were led to a quiet but radical idea. Space itself is not nothing. It has structure, it has conditions, it can carry influence. A field is our name for that structure. It is not a trick for calculation, and it is not a ghostly substance floating between objects. It is the way nature organizes cause and effect locally at every point in space. Something is defined, and objects, when they appear, respond only to what is happening where they are. No mysterious reach across the universe, no instant messages through nothingness, just space behaving in a particular way at everywhere. Once we accept this, the old picture begins to dissolve. Particles stop being tiny solid actors, pulling strings from afar. They become events, localized, quantized behaviors of underlying fields. Matter is no longer the foundation. It is a manifestation. What we thought were things turn out to be patterns. This does not make the universe less real. It makes it more coherent. The same idea that explains magnets and light also explains gravity and the shape of space, time itself. The same framework that describes empty space explains why it is never truly empty. The final question, physics, leaves us with what looked like a collection of separate phenomena becomes a single, connected story. And perhaps the most important lesson is not technical at all. It is a lesson about understanding. Nature does not care about our intuitions or our preference for solid objects and simple pushes. It does not arrange itself to match everyday experience. But it does offer something better, consistency, if we are willing to follow the logic carefully and accept ideas that feel strange at first. The pieces fit together. So the next time